Okay, welcome everyone to this week's edition of the HoloTube Seminar series. We are very happy to have Zohar Komargodski for the talk today, for the speaker today, and the stage is yours.
Thank you so much. Can you hear me now?
Yes, and we see your screen.
Okay, great. Thank you so much for coming. I'll try to give a somewhat improvisational talk on the high temperature limit of quantum field theory. I'll start with some observations from holography, thermodynamics. I'll then quote some general results that are pretty easy to obtain. I'll discuss a counterexample, some open questions. I'll base this talk on several papers, which contains subsets and supersets of these authors. And then I'll also mention some results by other people. Maybe some of them are in the audience, by Bushel, and I'll also mention some other results by subsets of these authors on the first line, and some other collaborations that have found relevant results in this field, I believe. But okay, and secondly, if there are any questions, please interrupt me at any point with whatever comments or questions you might have or corrections. Okay, so let me start with some general motivation. So if you look at any pretty much ordinary quantum phase transition phase diagram, so quantum phase transition, or in fact any statistical system that is familiar from your studies or from the lab. So there is typically some parameter that's some coupling in the Hamiltonian, and as you change this parameter, the system might go from a superfluid phase to a normal phase, or a superconducting phase to a normal phase. There are various sorts of phase transitions. So there could be some phase transition point. And then there could be a temperature axis, since this is a zero temperature. So this line is like a zero temperature phase transition. Or you can think about it as a statistical phase transition. It doesn't really matter. Then there is the temperature line. And typically what happens is that if there is an ordered system, let's say on one side of the transition, and a disordered system on the other, disordered phase and ordered phase on one side and another side of the phase transition, typically what happens is that the phase diagram looks like that. So once you go to very high temperatures, you're in the disordered phase. So you're continuously connected to the disordered phase, where the one-point functions of all order parameters vanish, and all the symmetries are respected. So this is something that we expect from thermodynamics. Let me just remind you an argument from high school, essentially, for why this is the kind of phase diagram you expect from thermodynamics. So we were told in high school that if you are at finite temperature, instead of minimizing the energy and finding the ground state of the Hamiltonian, we must minimize the energy minus the entropy times the temperature. And then people will tell you that if you take the temperature to infinity, or to be just very large, compared to all the scales in the problem, then you should maximize the entropy. And then the next step is that people would say that S is maximized, the entropy is maximized in states which are disordered. Because ordered states, you imagine a system of spins, all the spins are pointing in the same direction, and you imagine that therefore the entropy of the system is somewhat low, because all the spins are lined up, so there is not much phase space. So the idea is that S is maximized in disordered phases, where no order parameters have a VEV. And therefore, you expect that at high temperatures, you would always be in a disordered phase. That's a standard argument from thermodynamics. Now, let me mention a loophole. I'll show you a counterexample, actually, so you can ask, how can it possibly not be correct, this high school argument? So this argument has a very obvious loophole. that I want to explain now in 1 minute. And for this reason, I don't view this argument as a serious argument, even though I've heard it in school and undergrad, and it's in all the textbooks. So the real loophole in this argument is that, as you know, in near the phase transition, you have something like a conformal system. So the free energy scales like the volume of space. Okay, so the free energy of a disordered phase scales like the volume of space with some coefficient, let's say for the disordered phase, and the free energy of the ordered phase scales with possibly a different number times the volume of space. However, if you're talking about the breaking of a global symmetry, the contribution to the entropy is sub-extensive. So the whole question of spontaneous symmetry breaking contributes sub-extensively to the entropy. So it doesn't actually matter for the volume coefficient whether the symmetry broken or not. You know, if you have two phases of matter, which may or may not be degenerate, let's say you're at the phase transition point, whether there is Goldstone bosons in one vacuum and compared to the other vacuum doesn't even matter, because they don't contribute extensively, not in a, not in an important way. So really symmetry breaking is not the issue, but this is still an argument that's in all the textbooks. In holography, this is very obviously not the issue, because in holography, when you compare phases with given boundary conditions in ADS5, whether or not there is some, pion or Goldstone boson in the geometry, contribute something that's very subleading. Typically, there could be n squared degrees of freedom. A pion could contribute something of order 1. It's not going to decide the dynamics at large n. And if we're talking about discrete symmetry breaking, then even at finite n, this seems to be completely irrelevant. So while this is an argument from all textbooks, I don't believe it holds water, actually. Definitely not for discrete symmetries, and for continuous symmetries at large n, it's likewise not very impressive. But anyway, this is something that you would find in all the textbooks. So another argument for why this is the correct phase diagram in all the systems that we know comes from holography. So holography provides us with a toy model where we can analyze the spontaneous breaking of the U1 symmetry. That's the holographic superconductor. Okay, this is the holographic superconductor. In this superconductor, you can do many things. You can turn on a chemical potential. You can just turn on a temperature. So, well, typically, let's say that this is the chemical potential, or so let me just mention the simplest example of a holographic superconductor, which is in the original papers on the subject. So there you would essentially find that as a function of temperature, there are two fluids and a spontaneously broken U1 symmetry at low temperatures. There is a special temperature then in which this Reisner-Nordstrom type black hole doesn't have hair anymore, and then there is just one normal fluid, and this is just a standard superfluid transition. And so at high temperatures, it's completely disordered. There is no more hair. So actually, the holographic interpretation of why materials behave in this fashion, that at high temperatures they're always disordered, is essentially just the no hair theorem. Okay, so the holographic no hair theorem just says that if you take large Reisner-Nordstrom black holes, they have no hair. That's all it says. As far as I know, this is correct. If you look at the review of Sean Hartnell, they quote a no-go theorem that says that under some assumptions about which scalar fields are allowed to couple to this black hole, they don't develop hair. Of course, it's not a full proof, because there could be many other couplings that they've not considered, but at least for a large enough class of couplings, there is a no-go theorem in holography, and it seems closely connected to this question of why these phases are always preferred. In addition, Recently, there's been a lot of work by several people, but mostly by Alex Bushell, who I think reinvestigated many geometries such as Klebanov-Strasser geometry, and he found that indeed there were no clear counterexamples, even when you go beyond the assumptions that go into the no-go theorem that was quoted in the review by Sean Hartnell. So it seems that there are some inconvincing arguments from thermodynamics, maybe a slightly more convincing arguments from holography for why this should be the case. And it would be nice to know in field theory whether this is correct or not. So now I'll tell you a little bit about the field theory side of this problem. And I'll try to prove some general theorems, but actually then I'll give you a counterexample in fractional dimensions. And I'll emphasize that the problem for integer dimensions is still open. I'll give an example for fractional dimension, for Wilson-Fisher fixed points, essentially, which live in fractional dimensions like 4 minus epsilon, for finite small epsilon. Are there any questions about the introduction and the definition of the problem of what we're interested in?
Yes, so I would have, yeah, maybe that's actually relevant for the quantum field treatment, but I would have guessed or expect that at high temperature the system is critical because the temperature is the only scale in the system. So it's like a thermal, it behaves like a thermal CFT. But now you argue it would be like in a disordered phase, which is different.
A disordered phase is a phase where all the correlators decay exponentially, like in a thermal CFT, and the one-point functions of all charged operators vanish. So, like if there is an operator charged under U1 symmetry, its one-point function vanishes. So when you take, okay, so give me maybe one sentence, I'll say 2 sentences, and then we can maybe discuss it in more detail, because now I'll give you a very precise mathematical definition of what I mean by gap, disordered. I'll just give you a mathematical definition. Well, not mathematical, I meant a very precise physical definition. So a more precise definition, just give me 1 second and then I'll open the 4 questions again. So I'll consider a conformal field theory that lives in these space-time dimensions, okay? I want it to be unitary and local, but it's very interesting both for experiment and just as a theoretical question to try to relax these conditions, because many systems that arise in condensed matter are not necessarily unitary and local in our sense. Okay, so let's consider a conformal field theory in D dimensions. I would like to require it to be unitary and local for the meantime. And I would like to ask, let's suppose that we put this theory at finite temperature. Now, as you said, since the system at 0 temperature is critical, the temperature is the only scale in the problem. So I don't even have to talk about high temperature, low temperatures. As soon as the temperature is non-zero, I'm done. I'm not turning on any chemical potential, so I don't have a dimensionless ratio. There is only one scale. So we take a conformal field theory in the dimensions, we turn on a non-zero temperature, and we ask, can it be that the one-point function at finite temperature for some operator which carries some, let's say, Z2 quantum numbers or U1 quantum numbers is non-zero? Can it be? Okay. Now, this operator could be an order parameter for Z2, for U1, for SOM. I don't care at the moment. It's some operator that is charged under some global symmetry. It could be any global symmetry. Now, I would argue that if you find such an example, it would be just shocking in integer dimensions. We found a counterexample in epsilon, 4 minus epsilon dimensions, but if there is such an example in 3 dimensions, that would be really shocking, because it would mean that once you embed that conformal field theory into a 0 temperature phase transition, so if this is some parameter coupling G, and this is where your CFT lives at 0 temperature, if it still breaks a symmetry at finite temperature, it means that actually, if this is a disordered phase and this is an ordered phase, it means that the line would actually go, sorry, the opposite. The phase transition line, so it was the opposite in the previous picture. Let me just stick to my previous conventions. It was ordered here, disordered here. So it would mean that the line goes this way, because once you just go straight up from the CFT, you're in an ordered phase. So that would be just insane. Like you don't see such materials in nature, which if you heat them up, they remain in a symmetry broken phase. Okay, it always goes the other way. The line always goes the other way, which means that few examples like that exist, if any. And perhaps there is a theorem that forbids such examples from existing in the first place.
And if you would start with a massive quantum field here, so not like to the left or right of the this critical point that you have drawn, I would have guessed that you then also enter a critical regime at higher or at high temperatures. But this also seems to be excluded by your phase diagram.
No, that is basically what you say is basically correct. So when you go to very, very high temperatures, somewhere high up here, you're basically studying the physics of the conformal field theory. And if the conformal field theory breaks a global symmetry, then you're basically in an ordered phase. If it doesn't break, you're in a disordered phase. So that's why I'm saying that as soon as you learn something about this conformal field theory, whether this can be true or not, you can know whether the line is going to bend to the right or whether it's going to bend to the left. Because that's exactly what you said, that if you go to high temperatures, you're in the critical conformal field theory at finite temperature regime. So that's how I know from the computation in the conformal field theory whether the line is going to bend left or right. In all the experiments that you know, the line always bends to the left. It never does this. So this never happens. In simple magnets, simple quantum phase transitions, this never happens. This is because in a conformal field theory at finite temperature, basically you never get a one-point function that's non-vanishing for an order parameter. As far as I know, I don't think there is an experiment that shows a different behavior.
Can I? Hi, Zohar. Just a small comment. It's not phase transitional, but if you take tidal fermions or even Dirac fermions, and there is this thing like this kind of vortical effect or kind of magnetic effect, right? And there's a contribution which goes like t squared. So if you put masses to the fermions that at low energy, you wouldn't have it because the theory is the fermions are gapped, you won't see anything. But if the temperature gets higher and higher than mass, much higher than the mass, then this say axial current would switch on and would go like t squared.
That's correct.
Magnetic field or so. It's not, but it's a little bit like this, but I don't think it's symmetry breaking.
Well, this is just a reflection of what Johannes just said, that if you go to very high temperatures, the physics is dominated by the underlying second order phase transition at 0 temperatures.
Mm-hmm.
So your chiral fermions can be viewed as a second order phase transition between massive fermions, and maybe massive fermions with a negative mass. You can change the mass, and at some point you hit m equals 0. Okay, and so the physics at high temperatures is going to be very similar to the physics of massless fermions finite temperature. When the temperature is much bigger than the coupling, to some power to fix the dimensions, you're basically doing studying the physics of the conformal field theory at high temperature.
Right.
So I definitely agree.
Okay.
However, in the example that you said, there is no order parameter that has a VEV.
That's right. Yeah.
So it's not an example of symmetry breaking.
Yeah.
It's just you're basically computing some conductivity, and that agrees with the conductivity that's in the conformal field theory at finite temperature.
Okay, thanks.
Any other questions? Okay, I'll try to quote some now theorems. So theorem 1. This is essentially due to Coleman. Some people sometimes add Mermin Wagner, but there are other people involved also. So what does the theorem say at 0 temperature? Let me just quickly remind you. At 0 temperature, this is a textbook theorem. The theorem says that if the number of space-time dimensions is 2, then no continuous symmetry can break. What does it mean technically? Technically, it means that the one-point functions at 0 temperature of all operators charged under U1 or any other continuous group vanish. Another thing that this theorem means, which is not due to Coleman, I think it's probably due to Landau, but I don't know exactly who came up with this, is that if you're in one space-time dimension, namely just quantum mechanics, then it's kind of true that the one-point function of all charged operators vanish for all symmetries. So in quantum mechanics, there isn't even symmetry breaking for discrete symmetries, okay? Now, okay, this is a statement about quantum mechanics, and you know it from grad school that if there is such a potential, the wave function of the ground state is a symmetric sum, and so it's Z2 invariant. Okay, now both of these theorems have lots of little exceptions that I'm not going to discuss, but they mean something for non-zero temperature as well, and that's what's interesting for us in this talk. So if you take a system in these space-time dimensions and you turn on non-zero temperature, that's very similar to putting the system on a finite size circle of radius 2 pi over the temperature. So it's we basically put the system on a circle of radius 1 over the temperature to be careless about pi's. And therefore the number of non-compact non-compact dimensions has reduced to d-1, and we can therefore use these two theorems to make some comments about symmetry breaking at finite temperature. So if the temperature is non-zero and the number of space-time dimensions is any number smaller or equal to 3, that means that no continuous symmetry breaking can take place, can occur. If the temperature is non-zero and the number of space-time dimensions is smaller or equal to 2, then no symmetry breaking can take place. Okay, so this is just an upgrade of the very familiar Coleman et al. Theorems to finite temperature. In particular, the first statement means something that you all know from holography. It means that there is no superfluid-fluid transition in ADS4. So if you look at the superfluid-fluid transition, it's a U1 transition, and therefore it's forbidden. And this cannot happen in ADS4, which is dual to three-dimensional conformal field theory. So there's no superfluid-fluid transition in ADS4. And indeed, if you look very carefully at the holographic constructions of the superfluid-fluid transition in ADS4, it seems like there is a phase transition, but actually it's in the BKT phase. So it's not a strict phase transition. And to see that it's in the BKT phase, you have to take into account 1 over n corrections, I believe. So it's not a strict phase transition. This is unlike the superfluid-fluid phase transition in ADS5, which is perfectly kosher. It's a completely standard first order phase transition. But in ADS4, it's not. Okay, so when we look for counterexamples, we ought to have in mind these two facts, that we should look at high enough dimensions so that this is even possible theoretically. We could also be interested in different variations of this question. So I'm having in mind here finite n. If you want to study field theory strictly in the infinite n limit, then there are already counterexamples in the literature in 4 and 3 dimensions. But if you really want this phenomenon to occur in a physical system at finite large n, then I think it's more challenging. Also at infinite n, you can avoid these Coleman-like theorems, as you well know. Okay, are there any questions about this? I'll go to the next topic if not. My next topic is some class of models that we have studied, and I'll tell you what we have learned about this class of models. So this is a very basic question, trying to understand the quantum field theory avatar of the no-hair theorem, but I believe the question is open completely now, and we've just learned something about a counterexample in fractional dimensions. which is still very strange that it exists, and that's why we wrote the paper, but it doesn't settle the question in integer dimensions. So let's talk about the class of examples. This is a very famous class of examples of conformal theories. This is due to Wilson and Fisher. These are the most well-studied conformal field theories, perhaps. So we just have a bunch of scalar fields and an arbitrary quartic potential. Where lambda is completely symmetric. Okay, and the number of space-time dimensions is 4 minus epsilon, where Wilson and Fisher famously proved that there are calculable weakly coupled conformal field theories that you can systematically study. So this is a class of models. It's a huge class of models. In fact, it's not even completely classified, where you can ask whether you can try to plot their phase diagram. That's what we did in the paper. We just try to understand their phase diagrams. They have disordered phases, they have ordered phases, and then they have a fixed point, which is the Wilson-Fisher fixed point that separates those phases. And we just try to calculate whether the line goes this way or this way and look for counterexamples. Now, your first intuition might be that there won't be any counterexamples to the common law that the disordered phase dominates at finite temperature, high temperature, because these examples just describe magnets, such as the XY model, the Ising model. These are all subsets of these theories, and these are very well studied experimentally. And it would be strange if the phase diagrams would disagree. But there are many more field theories or conformal field theories that are described within this class of models. So it's not obvious that indeed none of them would work. Okay, so how do you find fixed points? You have to find fixed points. You have to set the beta functions for lambda to 0. You have to look for solutions of this equation. And the equation that you get is something like lambda I, j, k, l. I'm being very schematic without coefficients. You can find all the coefficients in the paper. So to solve this equation, you have to solve that lambda is, say, epsilon over 16 pi squared. This is very schematic. I don't guarantee that any of these coefficients are correct. So ij mm, then kl nn, sorry, nn. And then there is another term, which looks like ij m and then lambda k l m, and I think now there is p, and you sum, and you have to sum over the indices that are repeated. So the bottom line is that one term like this is kind of money. Just let me just slow down for a second and explain what we're doing. So there is some kind of horrible quadratic equation for the lambdas that you must solve in order to find fixed points. Once you find the fixed point, you can ask what happens when you turn on finite temperature. Okay, you have to do another computation, and then you can try to draw the phase diagram. So this is step one. Step one, we find fixed points. Step two, we put the system at finite temperature. Step three, we compute the one-point functions of various operators that are charged. These are O are some local operators charged under some global symmetry G. G is a global symmetry of the corresponding scalar potential. So therefore G is a subgroup of the maximal possible symmetry of scalar field theory, which is just On, where the index I goes from 1 to n. So we have n scalar fields. Okay, so this is a three-step process. You can just put it on the computer. One, you find fixed points, then you calculate their properties at finite temperature. The calculation of their properties at finite temperature is a completely straightforward exercise using the Matsubara expansion. So you can compute all the conductivities, the 1-point function, whatever you want. You can compute the thermal mass, the Debye screening length, all this stuff you can compute using the standard Matsubara expansion, because everything is weakly coupled because of this epsilon. And finally, once you understand well the finite temperature, you can just ask, is this system in an ordered phase or is it in a disordered phase? Okay. So it's a 3-step process. You can put it on the computer and start searching for interesting models. We did not do it that systematically, but I'll tell you what we found. If there are any questions about what we're trying to do, what are the actual computations, I'm happy to answer them. So before I tell you the results of this study, let me just give you an example. The simplest example is, of course, the ON model, which has this scalar potential. So in components, it's just sum phi squared. This is the maximally symmetric possible scalar potential. There is some coefficient lambda. It preserves the full ON symmetry. And there is a fixed point in the epsilon expansion in this class of models that was found in by Wilson and Fisher. So this is probably one of the best studied fixed points in the literature. People have studied it not just to leading order in epsilon, but probably already to sixth order in epsilon. And then you can compute the expectation values of order parameters, like phi. This is an order parameter for ON. And of course, you find that as soon as you go to non-zero temperature, it's 0. So this is the simplest example. You can just check it by following this 3-step procedure. It doesn't break any global symmetry at finite temperature. And that basically explains why simple magnets like the Ising magnet, the XY magnet, and others are in a disordered phase at high temperature. Actually, there is a more general theorem. There is a more general result that I want to phrase now, because I think it's important to understand why it's so common, this phenomenon. I believe it's due to this more general result, at least partially. So let's say that the symmetry that's preserved by your fixed point is G, and it's a subgroup of ON. If G is equal to ON, then it must be this, and the story is clear. But let's assume it's a subgroup. So the result says that the result that we proved says that if G is big enough, and I'll define what big enough means, then we prove that all the 1-point functions of all order parameters, for all the possible order parameters of G, they vanish at finite temperature. So O is any order parameter for G. Okay. Now I have to tell you what big enough means, and then I'll stop for questions. So big enough technically means that the fundamental representation of ON, namely just the vector, is irreducible under G. So when you try to branch the fundamental representation in terms of G representations, you just get one term in the branching, and that's it. Now, this sounds like a very restrictive condition for being big enough, but actually, if you look sociologically speaking, it covers a huge number of examples. Let me just list a few. Of course, it covers the original ON models. It covers the tetrahedral models, which are very famous magnets. It covers the Michel fixed points, which again, there's a lot of literature about them and also experiments. It covers the MN models, which again are very famous in condensed matter, and even more. So this one restrictive condition covers, I think, a lot of the experimentally studied quantum magnets. And maybe sociologically speaking, that's why we think that this is a generally true result. At least it holds for this class of models. And they cover a lot of the experimentally studied ones, so it seems good enough. But it's still not, from the QFT point of view, why would you assume that? What if G is not big enough? Are there counterexamples then? Are there any questions about this statement? Let me just see if there's some. Okay. So I'll move on. So the answer is no. And that's why we wrote a paper about it. I believe it's the first example in the literature. So we found a class of models that I'm going to say a few words about now, which behave very counterintuitively. So these models are called the OM times ON models. People also call them the biconical models. Obviously, such models don't have a good holographic dual, being that they're vector models of the Wilson-Fisher type, but nevertheless, as quantum filters, they're perfectly well defined. So they have three couplings. Sorry. I'll just be quick about it. It's not. So there are two vectors. One is an OM vector and one is an ON minus M vector. So there are three possible terms. And what we did was to just study these models very systematically. We studied the zero temperature fixed points. So the zero temperature fixed points exist. You can establish them. You can establish their existence both numerically and analytically, which we did in the paper. Furthermore, you can study the finite temperature behavior of this model. And lastly, you can ask whether this model leads to symmetry breaking at finite temperature. So this model has several interesting order parameters. In fact, at least two. This is an order parameter for the breaking of OM, and this is an order parameter for the breaking of ON minus M. So let me just quickly tell you what we found. What we found is that if the symmetry group is OM times ON minus M, then it's broken to ON minus M. I'm sorry, I'll fix it. It's broken to OM minus 1 times ON minus M if M is smaller than N. It's broken in the other, it's smaller in the other way. It's broken in the other way if M is bigger than N minus 2. And if it so happens that N is even and M is exactly N over 2, then it's unbroken. All right, so I believe that, well, these two cases are of course symmetric because you can exchange who you call M and who you call N minus M. But the bottom line is that if the two ranks of the two groups are not exactly the same, there is symmetry breaking in this model, and therefore there are Goldstone bosons. There are Nambu Goldstone bosons at finite temperature. There is no Debye screening because the finite temperature spectrum is gapless. And furthermore, well, there is hair. You can say that there is hair at the high temperature. There is no black hole here, but I'm still using the word hair to refer to symmetry breaking. Okay, so I believe these examples exist. They're the first examples in the literature. And now I'll just tell you a few words about what actually we know about 4 minus epsilon. They exist in 4 minus epsilon dimensions, but what do we know about which epsilons are allowed? So let's say that epsilon ranges from 0 to 1. These are the interesting values of epsilon, since we want to understand field theories between 4 and 3 dimensions. So clearly when epsilon is 0, we're talking about a 4-dimensional field theory. And in that case, the fixed points are all at the origin. There are no biconical fixed points. These are infrared free theories. And so there is nothing to say about 0. these are not examples. These are not good examples at strictly 4 dimensions because they are free. However, there is a regime of epsilon, which we can actually compute exactly, where there is symmetry breaking at finite temperature. So there are counterexamples here. Now, you can ask, does this interval extend all the way to 4 minus 1 equals 3 dimensions, which is perhaps the most interesting case since it lives in integral dimensions, and it could be an interesting construction of quantum magnets. Okay, so here I have to refer back to the Coleman theorem. Notice that this symmetry breaking pattern is of a continuous group for generic M. So for all M, which is bigger than 1, we're talking about continuous symmetry breaking. And this is disallowed in 3 dimensions. So therefore, for M bigger than 1, definitely this regime does not extend all the way to 3 dimensions. So we have not constructed an example in strictly 3 dimensions. You can ask, okay, what about M equals 1? For M equals 1, we have O1 times On minus 1 spontaneously broken to nothing. To nothing times On minus 1, namely On minus 1. So this is the same, this is isomorphic to Z2 breaking to nothing. And this is actually mathematically allowed in 3 dimensions since it's a discrete symmetry breaking in 3 dimensions, which is not disallowed by the Coleman-like theorems. But for this case, I would say it's a very interesting case. It's the best candidate that we've found in that paper, but we don't know. We were not able to prove or disprove whether this model breaks symmetry in strictly 3 dimensions or not. Now, let me explain why we don't know. To understand exactly if this regime continues all the way to 1, you have to do some computations in these models exactly. And it's very hard to do them exactly, of course. You need to resum the full series in epsilon. So instead, what you can try to do is you can start a 1 over n expansion to try to determine what's going on. But there is a very nice paper by Smolkin and Goichman that appeared very recently, which tried to study this question, in fact. And what they found is that the corresponding term in the 1 over n expansion that would decide whether this model is the first counterexample in integral dimensions or not happens to vanish for no good reason. So they found that some term in the 1 over n expansion vanishes. And so at the moment, the question depends on the next term in the 1 over n expansion. And we don't know whether it's positive or negative or vanishing. And this is very puzzling. There is some kind of conspiracy here of why is it vanishing, it's not clear. So the bottom line is that within this kind of fixed points, the described quantum magnets, 4 minus epsilon Wilson-Fisher fixed points, there are counterexamples, but it's not known if they extend to integral dimensions yet. But they definitely exist in fractional dimensions. Next, I want to give you an update on what happens in strictly 4 dimensions in Beck-Zaks fixed points, in gauge theories, weakly coupled gauge theories. This is again some more recent work that actually I was not part of. This is Cho et al. And several other papers, also Sanino et al. I'll just give you a quick update. Are there any questions about the 4 minus epsilon expansion model before I go to the weakly coupled gauge theories? All right, so I'll go to the weakly coupled gauge theories. So these gauge theories are of the Beck-Zaks type. So they look like maybe SUN gauge theory plus some matter, such that the beta function is very, very small. And you can try to tune the amount of matter so that the beta function vanishes in a perturbative sense and construct some perturbative expansion. And again, this is a clear 3-step process that this gentleman carried out. The first step is to find fixed points by solving some algebraic equations for the coupling constants. The second step is to put these theories at finite temperature and then study the one-point functions of order parameter. So the third step is to study the one-point functions of order parameters for various global symmetries. Now, which global symmetries? It could be flavor symmetry, it could be baryon symmetry, it could be any symmetry. In the context of Klebanov-Strassler, if you are motivated by some holographic construction, it could be more like a baryon symmetry, for instance. So this is what they've done, and they didn't just look at SUN gauge theories. They looked at the more general quiver gauge theories with various types of matter fields. And I think what they found is very curious. So I'll just tell you what the bottom line is. So first of all, they found that if you just set n equals to infinity and don't ask questions about 1 over n corrections, there are tons of counterexamples. By counterexamples, what I mean, these are conformal filters, planar conformal filters that have hair all the way to infinite temperature. And they found lots of such examples. But very interestingly, which I think is the biggest hint that we've got that there is maybe a deep theorem in quantum field theory that this is impossible at finite n, is that in each of those infinite n examples, when they took n to be finite but very large, this was washed out. Now, by washed out, what I mean, I want to explain technically how is it possible that at infinite n it breaks a global symmetry, but at large finite n it does not. So strictly speaking, they found lots of field theories which at infinite at infinite n have an exactly marginal parameter, exactly marginal coupling lambda, and at some point or maybe some interval on this space of exactly marginal couplings, what's called the conformal manifold, there is symmetry breaking. So here there is symmetry breaking at finite temperature. But as soon as you go to finite n, these exactly marginal parameters typically disappear if the theory is not supersymmetric. And instead, you just have some isolated points, maybe some isolated points which survive the finite n corrections. And those isolated points were always away from the regime where there was symmetry breaking at finite temperature. So as soon as they went to finite n, the effect was washed out, unfortunately. And so there is, again, no, strictly speaking, kosher finite n counterexample at in other words, there is no example where the order parameter is non-vanishing in finite n. So this fact, together with this mysterious vanishing that was found by Goichman and Smolkin, I think there are extremely suggestive hints that maybe there is really a no-hair theorem in QFT. Because all these constructions fail for various technical reasons as soon as you go to finite n or to integral dimensions, and it's very strange. So if you're in fractional dimensions, there are perfectly legit counterexamples already. If you're at infinite n, there are also perfectly legit counterexamples. But as soon as you try to go to physical number of dimensions and finite n, for some technically disparate reasons, these various constructions don't work anymore. So I think it's very suggestive. And I'll just close with some comments about holography, a few more comments about holography. I think in holography, the question of the no-hair theorem that was established by the ADS condensed matter community, of which I guess many of you contributed to, this relies on some simple setups like Reisner-Nordstrom black holes coupled to some scalar fields phi of various mass in ADS 5, let's say. But there are many things you can consider instead. You can consider double trace deformations. You can consider baryon-like symmetries, which you cannot describe in this. You can consider something like the Karch-Aharoni setup, where ADS spaces are glued together So there are many things you can consider which would try to go away from those assumptions. But I believe that, for instance, in the papers of Bushel, at the end of the day, when he looked at some examples, again, there were no strict counterexamples. But just as a curiosity, I will say that in these constructions that they found, the symmetries that were broken were baryon-like. Not ordinary flavor symmetries, but baryon-like symmetries. So perhaps this suggests a way out. Yeah, in any case, this is more or less all I wanted to say. If there are any questions, I'm happy to try to address them. But the bottom line is that there are some counterexamples now, which is very surprising that they even exist in the first place. But there is no counterexample in integral dimensions, which is purely fully unitary and finite n. So that's the end.
Thank you very much. That was a very, very thought-inspiring talk and a nice update. Anybody have any question?
Can I make some comments? Oh, hi Zohar. So thanks for a very nice talk. It's actually very nice that well, I don't understand why there is this conspiracy that you talk about. So in a holographic constructions, even though you can construct some models of this type, so I'm still fighting even in a phenomenological holography to try to make them stable. So there are some instabilities that might or might not be cured. But I want to point out that somehow this mystery of what is a real extends to string theory. So I can pretty much know now how I can take a supergravity scalar potential that comes from string theory. And there is a well-defined procedure how you deform it in such a way that you develop a small parameter. The problem with constructing the hair in a holography, because it usually comes, if you try to do it straight away, you don't know where to look for. There is no small parameters. There is no well-defined perturbative expansion. However, there is a way to deform pretty much almost any supergravity potential in such a way that you can construct first this ordered hair, conformal ordered hair perturbatively, and then you try to follow back to a supergravity potential. And in all examples I know, and I have done it in a bunch of examples that are not published yet, you fail to do it. And you fail to do it precisely as you try to, approach the real top-down holographic potential. So there is this mystery that I don't know about. And so I guess I am very sympathetic to this idea that there might be some deep theorem that simply forbids it. And what I'm trying to say is that this is a broader theorem. That's kind of a theorem. Well, okay, broader or not, if we believe in a holography, then it's going to be the same. Yeah. But I think it's nice that this is an example that clearly distinguishes what is a real holography and what is a phenomenological holography, something that I like very much.
Yeah, thanks for the comment. I also sympathize with that. And I think that this year or 2 years that I've been thinking about it made me very much almost convinced that there must be a deep theorem in QFT that forbids that. For unitary integral dimension QFTs that are fully unitary and finite n. Now I can tell you, you ask which conspiracy. I can tell you about the conspiracy because people in the audience here who are experts in holography might understand this conspiracy. This is the Goichman-Smolkin conspiracy. I think it's probably, I also feel that this must have a deep explanation, but I failed to find it thus far. So you just take Vasiliev theory, okay? Or I like to think about it as a QFT, so it's an ON vector model, but I can phrase the conspiracy in both languages. You take a Vasiliev theory, ON vector model, and you compute the 3-point function of just the energy operator. So this has an expansion in 1/n. So the first term is of order n 3/2. Oh, sorry, I said 3/2 and wrote 3/5. And the next term is of order n 5/2, and so on. So there's some power series expansion, which actually is also interesting for bootstrap and experimental statistical physics because they measure this, they measure it on the lattice at finite time. Okay, so it has been long known from, I think, Itzikson Zuber. It must be Itzikson Zuber. Itzikson Zuber, that this coefficient is actually 0. The first coefficient is actually 0. And this was computed explicitly in a 1/n expansion by Itzikson Zuber. Then in the work of Yin and Jomby about Vasiliev theory, they reproduced this result. It's some coupling in Vasiliev theory. It's a triple coupling in Vasiliev theory that just happens to vanish. Now, a thing that I will not explain, but I'll just state as a fact, is that whether or not this m=1 example continues to exactly 3 dimensions depends on the next coefficient. It's not easy to see. I have a whole paper that we didn't publish proving it, but it will never be published because of what I'm going to tell you. So what is the fate of this m=1 model depends on the next coefficient that was never computed before. And Itzikson Zuber didn't compute it. Yin and Jomby cannot compute it. It's some complicated question about Vasiliev theory. And Goichman and Smolkin computed it for the first time, and I believe the result is correct. It was also checked by the group of Igor Klebanov and Jomby, and I think they have a few other consistency checks, especially connecting to various results of the group of Igor Klebanov. And amazingly, this is also 0. So the whole point of the paper that we were supposed to write was that m=1 will be decided by this coefficient, and if it's non-zero, we're done, but it actually is 0. And there is no symmetry explanation. Why do these coefficients vanish? It's not clear. There must be some reason for that. But because this coefficient happens to vanish, it's not decisive. So we don't know what's going on with m=1. So we don't have a decisive counterexample in integral dimensions. And for this, because this looks so ridiculous, I've begun to believe that maybe there is a deep theorem that forbids symmetry breaking at finite temperature.
Yeah, thank you. Just maybe one last. So you keep bringing up Klebanov-Strassler, which is one of the models where you have this funny phases, and however, and again, there is also a paper on my side here that I don't know if it will ever be published for precisely that same reason. You can try to do exactly, well, okay, you can try to do something simpler. You can try to say, can I turn off the mass scale in a Klebanov-Strassler while having that, while having that funny phase still there? And you can show that it will disappear. So it's more like towards the other conspiracy things that you were mentioning. Well, okay, it's not 1/n. It's like, the range where the funny phase exists sort of shrinks with 1/n. And so what I see here, this is a different way. So that's kind of a different handle, how you can construct what I call exotic hairy black holes in a holography and try to make them conformal. And so Klebanov-Strassler is a different mechanism. But again, if I try to make it conformal, the hair disappears before they become conformal.
Yeah, maybe I should have said Klebanov-Witten to be, maybe that should have been a better way of saying it, because Klebanov-Witten, maybe I should have said.
No. Well, I mean, for the hair, I do mean Klebanov-Strassler. So I do need, I do need whatever the 3 cycle and the deformed conifold and all of that. Yeah, but okay, thank you, Zohar.
Okay. Any other questions or comments?
I might have one, which you probably can easily shoot down. Then can we not somehow recycle the BKT idea and generate a order parameter associated with some topologically protected configuration? For example, a gauge field that is a skyrmion or has some topological charge, like if I think holographically.
Yeah, you're completely right. So one of the classes of examples you might consider are examples where this would be an order parameter for a topological symmetry. Okay. Mm-hmm. So the simplest example would be some kind of monopole symmetry for Chern-Simons theory in 3 dimensions or something like that. Yeah.
Mhm.
This class of models, so I cannot actually refute it because the weakly coupled Chern-Simons theories were not studied yet. You can repeat this 3-step process for a whole class of theories that wasn't done yet, which are just the Chern-Simons matter theories. You can try to look for weakly coupled fixed points. There is a very helpful paper from the 90s by Ivanov, a group of 3 Russians, Ivanov et al. I think it's Ivanov. It must also include Kazakov. I think Kazakov is on that paper too, where they basically gave you a way. They wrote the algebraic equations that you need to solve to study fixed points of Chern-Simons matter types. Then there should be some work done on how to put them at finite temperature, which wasn't done, but it will not be terribly difficult. And then you can study this problem for this class of theories, which would include the examples you mentioned. And this wasn't actually done. You know, if this again leads to all sorts of funny conspiracies, and there are finite infinite n examples which disappear at finite n, I think that will be very nice additional evidence that maybe there is a deep theorem.
Mhm. Mhm. Are there any other questions? I should ask while I'm thinking.
Yes, I have one. So is there some rationale for expecting that something like this could be 0 to all orders in 1 over n, but non-perturbatively non-zero in n, in e to the minus n, something like that?
Do you mean concretely?
I mean this smoking thing.
Oh, that's an excellent question.
Something that could be non-perturbative in gravity, like change of background.
So yeah, if we look at this object, this is a very interesting question, actually. If we look at this object and it has a 1 over n expansion, which is infinite, and we just know that the first 2 coefficients vanish, okay? We know that this is actually 0. There are 2 possibilities here, of which you already mentioned. 2 possibilities. I don't know the answers. I'm just going to tell you just some nonsense comments. So maybe it vanishes to all orders, and maybe there is a symmetry explanation. Maybe it can be understood in Vasiliev theory, okay? In that case, the answer must be non-perturbative in n. Okay?
Mhm.
And then it could be that just the next term is non-vanishing. It could be, in principle. Now, I want to make a comment about the first case. The first case would be, I think, extremely surprising because this coefficient was measured experimentally. So this is kind of very down-to-earth science because people actually measured it for these cases. It was already measured. It was measured both like in experiment, in Monte Carlo, and via the numerical bootstrap. And it's non-zero. And in fact, I even remember the value here. The value here was like not too far from 1 over 1 point. The value here in some normalization was not too far from 1.4. So it's not a small number by any means, but of course it's n equals 1. So you can do a silly exercise. You could take the 2 results that exist. You know, you have 2 numbers and try to interpolate to infinite n using 2 numbers. And well, David Pollan did that exercise. Maybe he added another number. Maybe he also used some n equals 3 from numerical bootstrap. So he tried to make the interpolation, and it doesn't seem to decay exponentially fast. In fact, David Pollan at the time found that it decays like this, which is inconsistent with the large n answer, which vanishes. Of course, there is no mathematical inconsistency here because lots of things would happen between 1, 2, 3, and infinity. But I'm just saying that the numerical bootstrap results for small values of n are not even really nicely consistent with what we know from Goechman-Smolkin, that this vanishes and this vanishes, and there is a puzzle. I think it's very puzzling. Usually, if you look at Wilson-Fisher, the whole reason that Wilson-Fisher became so famous, and also the Itzikson-Zuber expansion in 1 over n became so famous, is because many things worked very nicely. If you just take asymptotic formulas and you plug n equals 1, n equals 2, it just works very nicely numerically. But this doesn't. and I don't know what's going on. So I have no idea, really. I can point you to one fact, which is that this zero was computed by Itzikson Zuber. It's a well-known result. But there is a paper by Maldacena and Zhiboyedov about the Vasiliev theories, or theories with higher spin symmetry. And they gave a new proof that this has to vanish using higher spin symmetry. Their proof does not extend to the next order, but maybe this is the beginning of something.
And I have another question. Maybe you mentioned this in the introduction, but I arrived late, so I didn't hear it. If you think of a lattice system, the high temperature limit involves temperatures which are larger than the inverse lattice spacing, which is a regime which you cannot study in a continuum theory.
That's right.
So I was wondering what is known about theorems that some rigorous people could have proven about symmetry breaking in lattice systems with, I don't know, compact operators and things like that.
That's right. So this is a super excellent question. So if you have a lattice theory, it has a lattice spacing parameter A, which is fixed, and it has a correlation length parameter XC, which is much, much bigger. That's when we say that the lattice system is in a critical regime, right? So you can study temperatures such that the inverse temperature is bigger than the lattice spacing, but much smaller than the correlation length. This is the regime where what I said is true. Because this is the regime that we can use continuum quantum field theory to study phase transitions. Now you can ask, what do we know about this regime? Where you're much smaller than the lattice spacing. Indeed, if you look at the paper that we wrote with Choi et al., you can just look it up. We quoted the rigorous result by the lattice community, exactly as you anticipated. There are people who in the lattice community that prove the rigorous result. So they just assume that the Hilbert space is a direct tensor product of on-site Hilbert spaces. They assumed local Hamiltonian and made a few more assumptions that are standard in the lattice community. And they proved that all the one-point functions always vanish. So when you go to this extreme high temperature limit in the lattice sense, even higher than the lattice scaling, then there is no symmetry breaking.
Okay.
And this is extremely easy to understand intuitively. I can just say why this must be true. If you have a Hilbert space, which is a direct product, if you just have spins on the lattice, okay? And the Hilbert space is a direct product of the Hilbert spaces. When you go to infinite temperature, the density matrix becomes 1. Usually the density matrix is e to the minus beta h, but when beta goes to 0, it just goes to 1. In quantum field theory, this doesn't make sense, because what is 1? It's a conformal phase. But in the lattice, it actually makes sense. So all the sites decouple. Since the density matrix doesn't, this density matrix doesn't allow for sites to talk to each other. So all the correlators are on site. So that means that sites decouple, and therefore the expectation value of some order parameter, if this order parameter is localized on sites.
It's like in quantum mechanics.
Yeah, so this is 0 like in quantum mechanics, exactly. So the assumptions that you have to make is that the order parameter can be written as a direct sum over sites. This is true in most lattice systems. If you take Heisenberg chain, the antiferromagnet chain, this is kind of always true. The Hamiltonian is a sum over local Hamiltonians that are on site. The order parameters are sum over on-site order parameters. And then when the density matrix is 1, it just becomes trivial. So in some sense, it's a trivial theorem, but to prove it rigorously, you need some kind of mathematical formalism. So there is a rigorous paper that actually proves it, but I think it's physically obvious. And the reason that it doesn't happen in quantum field theory is because this doesn't make sense. And also in quantum field theory, it doesn't make sense to decompose the Hamiltonian in this way.
Right.
Great, thanks for the questions and for the answers. Are there more questions?
Okay, thank you so much.
Then thank you, Zohar. Thank you very much for your time. I will stop the recording, and everybody who wants to stay around, stick around. Thank you, Zohar, again for your talk and for your answers.